Now in this lesson, we are going to take up a good problem. There is a hollow sphere, non-conductor, and this is having an inner radius R1 and outer radius R2. Charge Q is uniformly distributed here because this is a non-conductor. Charge will not just reside on the outer surface, we can put it anywhere, so charge is uniformly distributed everywhere. So this charge is there everywhere on this, and it is uniformly distributed, say plus charge over the material of this hollow spherical non-conductor. Now we have to find the electric field at a distance x from the center, and this x lies between R1 and R2. So x is more than R1, less than R2. Charge that is there on this is capital Q. So capital Q is uniformly distributed over this material, which is a hollow spherical non-conductor. Inner radius is R1, outer radius is R2. So let us first calculate the charge per unit volume, rho. So charge per unit volume will be given by Q divided by the outer volume. Okay, outer volume will be 4 by 3 pi R2 cube, and you have to subtract the inner volume. Okay, volume of radius R1, spherical volume. So 4 by 3 pi R1 cube. So this will give us the charge per unit volume in this material. Since we want to find the electric field at a distance x, we'll draw a Gaussian surface of radius x, a spherical Gaussian surface of radius x. And we need the charge inside this Gaussian surface. Now the volume of material inside this Gaussian surface, that is this volume, the volume of material inside this Gaussian surface will be equal to, say we call it V enclosed, okay, enclosed by the Gaussian surface, will be equal to 4 by 3 pi, the outer radius cube, which is x cube, minus 4 by 3 pi R1 cube. Okay, and charge is there in this volume. Charge enclosed is there in this volume enclosed. So therefore Q enclosed will be equal to rho, which is charge per unit volume, multiplied by the volume enclosed. Okay, charge enclosed is Q by V into volume enclosed, volume of the material enclosed rather. So therefore this will become equal to Q. This 4 by 3 pi will cancel, okay, so you'll be left with R2 cube minus R1 cube multiplied by x cube minus R1 cube. So in this situation, the charge enclosed is so much. All those symmetry arguments are valid. Okay, E vector will be same at every point of the Gaussian surface. E vector and dA vector will be parallel at every point. So the electric flux will become E into A, and this is equal to Q enclosed that we have got divided by epsilon naught. A is the area of the Gaussian surface since it is spherical. a sphere of radius x, the area will be 4 pi x square. So therefore, E into 4 pi x square. Q enclosed is this. Okay, we can write that. Q enclosed E into 4 pi x square will be equal to Q enclosed by epsilon naught. Okay, that is what is Gauss law. So basically, the equation that we get is E into 4 pi x square equal to the charge enclosed by epsilon naught, so 1 by epsilon naught into Q, and the volume inside the Gaussian surface is proportional to x cube minus r1 cube, and the net volume of the material is r2 cube minus r1 cube. This is the volume of material inside the Gaussian surface, and that is the total volume of material 4 by 3 pi has cancelled from upstairs and downstairs. So therefore this electric field becomes 1 by 4 pi epsilon naught Q by x square, x cube minus r1 cube by r2 cube minus r1 cube. Some of you may find this question difficult. It's not difficult at all. Okay, we had a hollow non-conductor sphere, okay, and a charge Q was uniformly distributed here. So we found the charge inside this, okay, inside the Gaussian surface. How we found that? We knew the total charge in this material is Q. So we found the volume of this material by 4 by 3 pi r2 cube minus 4 by 3 pi r1 cube, and then we found the material inside the Gaussian surface 4 by 3 pi x cube minus 4 by 3 pi r1 cube. We found the charge enclosed. According to Gauss law, E into A is Q enclosed by epsilon naught. Okay, all the symmetry arguments are valid. A here became area of the Gaussian surface is 4 pi x square, and we got this electric field. Now, in the second part of the question, they want us to plot E as a function of R for R equal to 0 to R equal to 2R2. Now up to this R1, if you draw any Gaussian surface, the charge enclosed is 0. If the charge enclosed is 0, the electric flux is 0. If the electric flux is 0, then electric field is 0. So up to R1, the electric field will be 0. When we put R1 in this equation, now this equation is valid for x lying between R1 and R2. So when x equal to R1, then E is 0. We can check from this equation. When x equal to R2, E will become 1 by 4 pi epsilon naught Q by x square, because this will now become 1. So now this will increase and reach a maximum value at x equal to R2, which will be equal to, this you can call it Coulomb's constant, K Q by x square, or rather KQ by R2 square at x equal to R2. It reaches this value. Now we have to go up to 2R2. Outside, this will behave like a point charge at center. So therefore, we can just apply Coulomb's law. The distance is 2R2. So this will fall off as 1 over R square. And here at 2R2, the electric field will now become KQ by 2R2 whole square. So this is the ER graph in this case.